In this problem, we have a rod that is supported at points A, B, and C by smooth journal bearings and is subjected to the two forces shown. We're asked to determine the reactions at each of the smooth journal bearings. This is a 3D rigid body equilibrium problem. So we'll start by drawing a free body diagram, and we look at our supports and see that we have smooth journal bearings. And if we look in our table for support reactions caused by the different types of 3D supports, we would see that for a smooth journal bearing, and I'll use A for the example, for a smooth journal bearing, we would show a force, we'll call it A sub x and A sub z. We're going to have two of the force components that are possible. The smooth journal bearing provides no resistance to movement in the y direction, and we would have a moment component about the x-axis. In other words, rotation is restricted about x, and as well as z. So we would call those m sub a x and m sub a z. And the rod is free to rotate about the y-axis, given the definition of a smooth journal bearing. Now, so if we just had a single journal bearing, that would be how we would show the support reactions on our free body diagram. And I'm not going to draw a separate free body diagram. I'm going to use, for convenience, I'm going to use the figure here, but I do expect you on, in homework or on test or whatever to draw a separate free body diagram where you have the advantage of being able to draw neater with a straight edge and a pencil rather than on the iPad as I'm doing. So if this was just a single support, this is what we would show at A. But this is the case where what we have the case here that was discussed in lecture 12, where we have multiple journal bearings, and the force reactions alone at each of the three journal bearings are adequate to support the bar, the rod, and therefore these moments are not created. There are no moments created about the supports at A, B, and C. So let me erase what I have and go back, and armed with that information, realizing that I have the case where I have multiple bearing supports, and let me draw the support reactions, knowing that I that I only have force reactions, not moment reactions at each of the supports. So at A, I'm going to show on my free body diagram a reaction in the x direction and call that A sub x, and a reaction in the z direction and call that A sub z. Now notice here I've mixing it up a little bit. I've assumed that A sub x acts in the negative direction and A sub z acts in the positive direction. I may or may not be correct, and I'll know that when I solve for those unknowns and look at the sign in front of the magnitude. Okay, let's do B in a different color here. So I'm going to have the same situation at B sub x, B sub z, okay, and then down here at C, it's a different orientation, so I still have an x component, but then the second force component is going to be in the y direction. Okay, so if I remove that rod from the supports, from ground if you will, I would replace each support with the reactions caused by the support on the rod, and in this case it's going to, those reactions at each support are 2 force components. So I have a total of 6 unknowns here. I'm able to write 6 equilibrium equations for a 3D rigid body problem. So I should be able to solve for each of these unknowns. It's good to have some type of strategy, especially for what's going to be a little bit of a longer problem here with a lot of calculations to sort of figure out where should I start and where am I going. There's many different ways to approach this, which equation to write first. I'm going to start out here at the outermost forces, C sub x and C sub y, try to solve for them and sort of work my way back to B and then to A. But there are many valid ways to approach this problem. You probably want to start, just to get going, try to pick something that's an equation that's just going to have one unknown without a lot of calculation in it, just to sort of get going. So if I look between C sub x and C sub y, I notice that I can involve C sub y in a sum of the forces in the y equation. And I only have one other force in the y direction, which is that 400 newtons. Now I should be able to see right away that I've assumed incorrectly for the direction of C sub y, because C sub y is going to have to offset that 400 Newton force that's going in the positive y direction. So C sub y is going to end up going in the negative y direction. Let's see if that works out here. So some of the forces in the y direction would be a positive 400 newtons plus C sub y, the way I've drawn it. And then I solve for C sub y, and I get C sub y equals negative 400 newtons. So C sub y is actually going in the other direction. Now I'm not going to go back and change the free body diagram. I'm going to go ahead and leave it like it is, and just remember that this is what I calculated for C sub y. So I'm going to keep track of my progress here. So I have picked off C sub y with one equation, and next I'm going to focus on C sub x, and given my strategy, but yours could be different. And I'm going to look for an equation that I can involve C sub x in, or that would involve C sub x, where C sub x is the only unknown. So some of the forces in the x direction equal to 0, is a possibility, but if I do that, I've got not only c sub x as an unknown, but I have b sub x and a sub x. So that's probably not the first choice for c sub x, to include c sub x in an equation of equilibrium. So I study the figure some more and look at it and decide that, well, what if I sum moments about the y-axis? So c sub x is definitely going to create a moment about the y-axis. The only other force on the free body diagram that's going to create a moment about the y-axis is the 600 Newton force, shown here. The forces at A and B both act through the y-axis, so those will not create a moment about the y-axis. The 400 Newton force acts along the axis, so that won't create a moment about the y-axis. And c sub y, which I just solved for, acts parallel to the y-axis, so it also will not create a moment about the y-axis. So if I sum moments about the y-axis, the only unknown is going to be c sub x. Now I could do this in scalar, but I'm going to go ahead and do it in Cartesian. This one is actually fairly easy to do in scalar, but I'm going to go ahead and work through it in Cartesian. And I'm going to say that the sum of the moments about the y-axis equals 0, and that it's going to equal, remember our equation for the moment of a force about an axis is, and I'll write it right here, a moment about A was equal to U sub A unit vector along the axis, dotted into the moment of a force, the force about the axis, where r is any position vector from the axis to the force. Okay, well, in this case, my axis is the y-axis, which has a unit vector of j. So I'm going to dot j into the moment or moments about the y-axis caused by any forces that create moments about the y-axis. And I said that the 600 Newton force creates a moment about the y-axis. And in Cartesian, r from the y-axis to the 600 Newton force is 0.6 I. And I would cross that with 600K. Okay, and I'll put those in brackets for the time being. And then c sub x has a position vector of, put this in brackets again, .6 I, minus 0.4k. Okay, that's r from the y-axis to c sub x, and then c sub x, I have that drawn going in the negative I direction, so it's going to be r cross minus c sub x I. Okay, now let me get I'm going to put a bracket there, make this a little bit smaller, and then I'm going to put a parenthesis here. I think that'll work. Okay, now I could have used determinants for these, but I'm going to do it this way just to mix things up a little bit. This is perfectly valid, just as valid as using the determinants. So I'm going to reduce what's in here, work inside the parentheses and brackets outward. So I'm going to have j dot 0.6i times 600k. I cross k is negative j, and 0.6 times 600 is 360, so it's a negative 360j. Okay, plus 0.6i crossed into negative c sub xi. I cross I is 0, so that term is going to be 0. And then the next term is going to be negative 0.4 times negative c sub x, which is a positive 0.4 c sub x, but don't forget about the unit vectors. K cross I is also positive, so that sign remains positive there. And that is also j. K cross I is positive j. Okay, now for my dot product, I'm just going to have, let's not draw j again. I have j dotted into 360j is just j dotted into negative 360j is negative 360, and j dotted into 0.4cxj is just plus 0.4cx. Remember, it's just a scalar. Okay, so all that equals 0. So therefore, we can do the math and find out that c sub x equals 900 newtons. Okay, so I found c sub x. Next, I'm going to look at b sub z and try and find an equation that of equilibrium that just has only b sub z as the only unknown, and I can get that by summing moments about the x-axis. So sum of the moments about the x-axis equals 0 equals, now let's look at this here. How did I How did I get that? Well, if I sum moments about the x-axis, a sub z and a sub x either act along or through the x-axis, so they don't create a moment. So those two unknowns won't come into it. B sub x is parallel to the x-axis, so that won't come into it. And then everything out here on the right end of the rod, I already know. I know C sub y, I know C sub x, and I'm given the 400 and 600 Newton forces. So this is going to be a little bit of math, it's going to be a little bit of work, but we should be able to solve directly for B sub z if we can work through all that. Okay, so we said some of the moments about the x-axis equals 0. So in this one, I'm going to take a unit vector along the x-axis, which is I, and dot it into, now I'm going to have 4 terms here. I'm going to have the B sub z term. I'm going to have a term for the 600 newtons. I'm going to have a term for C sub y, and I'm only going to have 3 terms. I'm sorry, 3 terms. 3 of these forces create a moment about the x-axis, and they are C sub y, the 600 newtons, and B sub z. Okay, so I'm going to write R cross F for each of those 3 forces, R being a position vector from the x-axis to each specific force. So I'm going to have, I'll do B sub z first, 0.6 j crossed into B sub z, which is in the k direction. Okay. Plus, now let me look at the 600 Newton force. R for that, from the x-axis to that force, is 0.6 I plus 1.2 j, and that's going to be crossed into a positive 600k. And then the toughest one is going to be the, C sub y, and the position vector for that is going to have all 3 components. The position vector for that one is going to be 0.6 I plus 1.2 j plus, now C sub y, I left it shown in the positive y direction, which is how I originally drew it. When I solved for C sub y, I got a negative 400 newtons. So, you know, you have to decide, you're going to go back and change things, update your free body diagram, and then change the sign on your answer or not. I tend to leave the signs like they are, and then just, you have to remember to pick this up when you write further equations. So, and I'm sort of jumping the gun a little bit here. I didn't, I apologize, I didn't put my, this would be minus 0.4k, and I'm sorry, I jumped the gun there just a little bit. Now, C sub y is, I'm showing it in the positive direction on my free body diagram. I know it acts in the other direction. I've already solved for that. It's a known now. So I need to show that 400 newtons as a minus 400J. Okay. Now I'm going to do this one in a little bit of an abbreviated fashion here. I worked the first moment equation out step by step. I'm going to take some shortcuts here, and you should be able to do this at this point. 0.6J times B sub zk is going to be a positive 0.6 BZ I. J cross K is a positive I. Dotted with I just gives me 0.6 BZ. Okay. The second moment here, since I'm going to dot the result with I only have to worry about the results of this cross product that are in I. So in other words, 0.6I cross 600K is going to give me J, so I don't even have to do that one, because when I dot that with I, it's going to go to 0. But J cross K, I have to do that one. J cross K will give me positive I. 1.2 times 600 is 720. I dotted with I gives me plus 720. And for the last one, again, I only have to worry about the results of this R cross F, this moment, that are in I. So 0.6I crossed into negative 400J is going to give me K, so I don't worry about that one. J cross J is 0. And I do have to worry about this one. Negative 0.4K crossed into negative 400J. The signs on the numbers go to positive because of a double negative, but K cross J is a negative I, so that's like a triple negative there. And I'm going to write minus 160. All that equals 0. So therefore, B sub z equals, when you do the math, negative 933.3 newtons. Okay, so I assume the wrong direction for B sub z also. But I'm going to leave the free body diagram like it is, and remember that B sub z is acting in the negative direction. Okay, halfway there. These problems can be pretty involved. You have to keep your wits about you and do a lot of bookkeeping here. Let's look at so we have B sub z. Now that we have B sub z, we only have one unknown in the z direction, which is A sub z. So let's go ahead and solve for that one by summing forces in the z direction, which would be A sub z minus the 933.3 for B sub z plus the 600 newtons for the given force out at the end of the rod. And if I solve that for A sub z, I'll get A sub z equals 333.3 newtons. And that's going to be positive. So that one is shown correctly on the free body diagram. Okay, that leaves A sub x and B sub x. So it's not going to do me any good to sum forces in the x direction yet. So I'm going to have to write my last moment equation. I've summed moments about y, some moments about x, so now I'll sum moments about z. And if I sum moments about z, I don't have to worry about a sub z or a sub x. They act either along z or through z. B sub z is parallel to the z-axis. The 400 Newton force acts through the z-axis. The 600 Newton force is parallel to the z-axis. I do have to pick up c sub x and c sub y. They both produce a moment, separate moments about the z-axis, and that leaves me with just b sub x. So I'll have 3 moments to account for here about the z-axis, and the only unknown in writing those moments will be b sub x. So the sum of the moments about the z-axis, the unit vector is k. I'm going to dot that into, let's do b sub z first. The position vector from the z-axis to b sub z is just 0.6j crossed into, now I've shown bx in the negative direction, so it's going to be crossed into negative bxi. Then let's look at c sub x, which is 900 newtons in the negative I direction, but r to from the z-axis to c sub x, I'm just going to go from the origin out to the point where c sub x acts on the rod. So r is going to be 0.6i plus 1.2j minus 0.4k crossed with c sub x is 900 going in the negative I direction. And now c sub y is going to have the exact same position vector, 0.6i plus 1.2j minus 0.4k crossed into c sub y, which remember is negative 400j. Okay, now I only have to worry about the components, I only have to worry about the k components of the moments. So for this first one here, 0.6j crossed into negative b sub xi is going to be negative 0.6 b sub x j cross I is negative k, so there's a double negative there. So it will turn out being a positive 0.6 bxk, and when I dot it with k, the k's go away. Okay, so that's the first term. The second term here, I only have to worry about the second moment here. I only have to worry about the k components of that moment. I cross I is 0. J cross I is negative k. Negative 900 times 1.2 is going to be a negative 1080, but it's a double negative, so it'll end up being plus 1080. And the third term there, k cross I, is going to be j, so I don't have to worry about that one. Okay, the last term, the last moment, I cross j is a positive k. 0.6 times negative 400 is a negative 240. J cross j is 0. K cross j is negative I, and I don't need to worry about that. It's not a k term. So the right side of that equation reduced to these three terms. And I solve for b sub x, and I get negative 1400 newtons. Okay. Now I can write my x equation. I just have the one unknown left. I've solved for b sub x, and sum of the forces in the x direction is equal to, I showed a sub x in the negative direction, so I write negative a sub x. Now I showed b sub x in the negative direction, and it, when I solved for it, I got a negative 1400. That means that b sub x acts in the positive direction. This can be a little confusing, but you're going to have to come to grips with it and decide how you want to keep track of these things. This is the way I do it. You can do it differently, but as long as you do it correctly. So it's going to be plus the 1400 newtons, and then minus c sub x, plus c sub x, and c sub x is 900 in the negative x direction, so it's going to be minus 900. So I solve for a sub x, and I get 500 newtons. Okay, so that's a long one. Again, there's a couple different ways many different ways to do this depending on where you want to start, but in the end, you're going to be applying the 6 equilibrium equations for 3D rigid body equilibrium and solving for the 6 unknowns.